on blob-homology.
Thanks very much, John. And thanks for John and Julie for organizing a great session tonight. So this is a two-part talk. Kevin Walker is following up with part two in a moment. There are slides for both parts online, and there's a paper. The paper comes with a big warning on the front page that it's a draft, not actually a real paper yet, but you're welcome to read it if you'd like. The warning at the beginning points out the places you should be careful, things like that. Okay, let's get started. I saw this awesome quote in the last AMS notices from an interview with Yuri Manin from a year ago. You should read that. Be happy. Anyway, okay, there's the quote. Let me start telling you about this gadget, blob-homology. So it's actually that we build a complex first. So what is the blob complex? It's a gadget where you feed in an N manifold M and an N category with strong duality. I'll come back to that in a moment. C, and it produces a chain complex, the blobs on M with coefficients in C. And what I'm going to tell you first is not actually the definition of the complex, but a bunch of special cases of what you get from the blob complex that will convince you that this thing we're doing is connected to lots of other bits of mathematics that you already know about. It's a common generalization. So the first one, I guess, yeah, this is the first one. Okay, so we can take, this is the blob complex, and we can take the homology, and now we can just look at the zeroth graded piece of the homology. And I want to say that this is the usual TQFT Hilbert space associated to that manifold M and that N category C. I'll show you that in a little bit more detail in a moment. Specializing in a different direction, we can just look at the N equals 1 case. So now we might as well look at the circle, as our manifold, and our N category is just an associative algebra, or an algebra if you really want to have multiple objects. And the homology of the blob complex in that case recovers exactly the Hochschild homology of that associative algebra. So that's already two quite different directions. And there's a third direction which I'm not going to say anything about in this talk, but you can plug in, you can think of a commutative algebra, such as polynomials in one variable, as an N category in a sort of trivial way. And when you do that, so we're just putting in a really boring N category, you can recover some topological information about the manifolds, in particular the homology of the blob complex there picks up the singular homology of the infinite configuration space of the original manifold. And there are a few variations of this. Polynomials at multiple variables, and you allow inverses, and so on, and you get various other things down and so on. Okay. So the input for the blob complex is a manifold and an N category with strong duality. And having seen your guys' reaction to Chris's talk, I know that this is a very dangerous thing to say, because you're all well aware that N categories are dangerous ground. And so happily, the division of labor that Kevin and I agreed upon this afternoon is that I get to pretend that N categories are nice and easy and straightforward and everyone knows exactly what they are. And he's going to tell you the actual definitions that we're using in all of this, and you get to pepper him with the difficult questions about Morse theory and weak identities and all of that stuff.
And he's going to catch a bus and leave town.
No. Okay. So Kevin's talk, part 2, will explain this crazy notion of a topological N category. It's, in particular, this definition has duality built in very, very centrally in the definition. You can't talk about this notion of N category without having duals at all the different levels. And he's also going to tell you a little bit about an A infinity version of these N categories. Just like you can go from associative algebras to infinity algebras, there are A infinity versions of all of this. Well, okay, Kevin will say this stuff, so I won't bother going into anything more about N categories. From now on, they're nice and easy and well understood. Okay. In particular, actually, you should just think about, for the rest of what I say, pivotal 2 categories where everything is nice and safe. So let me remind you what a pasting diagram is. A pasting diagram on a manifold is just that you say we're thinking about some model of categories like what Chris was talking about, where we have bihedrons and higher dimensional versions of those. You slice up your manifold into a big collection of those glued together, and then you label all of those pieces of the manifold by a morphism from the category. So that's a pasting diagram on some manifold for a given category. And I'm going to start using the word field on M to just mean a pasting diagram on M in some fixed category. And I'll always assume that the top level of morphisms form vector spaces. So I'm going to always let myself talk about linear combinations of fields where I'm implicitly thinking that these pasting diagrams are multilinear in all the top dimensional cells. Okay, so here's an example. We could look at the temporally lead category, which is a lovely 2 category. And here's an example of a field on the torus. We've chopped it up into pieces. Don't worry too much that these are squares, not bihedrons. You should be agnostic about shapes for right now. And in each one of these pieces that is locally just a ball, we've drawn some morphism, temporally lead, and the whole thing is a field. Okay. Now, pasting diagrams on balls, we can say something special about. In particular, if you have a pasting diagram on a ball, you can do all the compositions and just get a single morphism on that ball. So in particular, that's a map from pasting diagrams on the balls to just morphisms. And we can think about the kernel. So here's an example of something in the kernel. In this example, this is a ball divided into 2 parts. In each part is some morphism from temporally lead. And I claim that these both evaluate to the same thing, the same morphism from temporally lead, just because this is just a single piece of string in temporally lead, and temporally lead is a circle is equal to D. So if we divide by it, these 2 things are the same. Okay. So we'll call linear combinations of pasting diagrams that evaluate to a zero morphism a null field on a ball. So this is something that we can only talk about the balls. Okay. So with that all said, here's a little bit of background on TQFT invariance from a slightly unusual perspective. So a decapitated n+1 dimensional TQFT is something that associates a vector space to each n manifold. And I say decapitated here because it's something that you don't expect to give numerical invariance of manifold 1 dimension up. The top level of it is the vector space. And you can, let's see. Let me maybe not say these things in the middle, you can read them if you feel like it, and just jump to the bottom and tell you how, in this setting, you expect to get a TQFT from an n category. You just look at the collection of all fields on your manifold, and then that's some gigantic vector space. But now we push it down by any field where inside some ball you see something that's in the kernel of this evaluation map, something that locally ought to be 0 in the category. Okay, and from this perspective of associating TQFTs to n categories, you get a fully extended TQFT that can associate something to every codimension manifold, and in particular it associates to the point in the original n category that you fit that. Okay, so now let's start talking about the blob complex itself. The idea is that we want to produce some complex so that when we look at just a ball, this complex is like a resolution of the TQFT invariant of the ball. That is, the homology should all be concentrated in degree 0 there, and it should just look like the morphisms of the category. Okay? So here's, so that's part of the motivation for how we like the blob complex to look. It should be something local so that we can define it on arbitrary manifolds, but only by ever thinking about things locally. And this is pretty much where you have to start. So the 0th graded piece of the blob complex is just arbitrary fields on a manifold. Again, it's a big giant vector space. The first bit of the blob complex then are linear combinations of triples like this, B, U, and R. B is just some choice of a ball embedded somewhere in the manifold. U is a field on that ball that is in the kernel of the evaluation map. And then R is just any old field in the complement of that ball. The differential then is just forget about the ball and paste U and R together to form a big pasting diagram on the entire manifold. It's easy to see that the quotient of B0 by the image of B1, or the image of this first differential here, is just what we said the TQFT invariant is meant to be. Just fields, what things that are locally in the kernel, have something in the kernel of the evaluation. So now, to do all the higher bits of the blob complex, pretty much we just do whatever we need to do to kill off any other homology that would turn up when we do this on the ball. So you think about what's in the kernel of D1 now, and just add more stuff in B2 that kills that up. So let's see what that turns out to look like. Here's B2. It's a direct sum of two pieces, the disjoint piece and the nested piece. The disjoint piece, the second piece of the blob complex, looks like this. It's linear combinations of I guess, quintuples here. It's a choice of two disjoint balls inside the manifold, a null field on each one of those balls, and an arbitrary field on the complement of the balls. The differential here is just a sum over ways of forgetting one of the balls and pasting together the other appropriate pieces. So in the first term here, we forget the ball B1, and so now the field on the complement of the ball that survives is just this null field B1 put together with R. And the other term, we forget B2, basically paste the other things together. The other part of B2 is the B2 nested. It's almost identical. Here we have two nested balls. The conditions here is that the innermost label here has to be a null field. The label on the annular region between the two balls can just be an arbitrary pasting diagram in that region, and then there's an arbitrary field on the outside. And again, the differential is the same. It's a sum over ways of forgetting a ball. The one thing to notice here is that in this term, where we've forgotten the inner ball, this composition, U composed with R prime, is still a null field because inside some smaller ball, it was a null field. And so obviously, anytime you take a null field, you can add more stuff on. Okay, so the last bit of the definition, you can probably guess from those pieces, we allow an arbitrary tree of K balls embedded in the manifold, which are either pairwise disjoint or pairwise nested. And we label everything inside by a field, and any innermost ball we label by a null field, some pasting diagram that evaluates to 0 in the capital. The differential is just sum of ways of erasing one of the blobs. Okay, that was the definition. And if you weren't scared by the end category part of it, then it's a very, very simple and straightforward definition. Let's now talk a little bit about the nice properties that it has. So this first slide on properties is just telling you a little bit more detail about something I said before, that when you plug in a circle, it specializes to Hochschild homology. So this is just reminding you a little bit about that setting. If you look at a TQFT invariant on a circle, well, our pasting diagrams for some associative algebra A, we might just think of as some dots on a one manifold, with each dot labeled by an element of the algebra. And so the TQFT invariant should be well, there's all fields on the circle, so put down a bunch of dots, however many you like, labeled by elements of the algebra. But then you mod out by things that evaluate to 0. And well, this is most of the things that evaluate to 0. You take a little interval with two dots labeled by two different things, or look at another picture with a single dot labeled by that dot that evaluate the same thing. You could also look at just differences of intervals with points in different places with the same label. So it's easy to see that this quotient here is just co-invariance of the original algebra A, because you can always combine all of your dots together, but you can always take a product, AB, put it on one dot at the top, and move the B around the circle to the other side. So this is the usual TQFT. On the other hand, the Hochschild complex is the derived version of co-invariance. You pick a projected resolution of A as an AA binomial and then take co-invariance of that. And there's one explicit way to write down that the derived version of co-invariance, and you can go and read a pretty icky proof in our graph explaining that Hochschild complex on A is quasi-isomorphic to the blob complex on the circle. And it's sort of it's a little bit of an unpleasant proof because it doesn't explicitly show you a map and then show that it's a quasi-isomorphism. It shows that both constructions have the same set of universal properties, so they must agree. What I've drawn here, though, is just a little bit of sort of the lowest degree of the map, or the second lowest degree of the map. Yeah. So what do you send this to? Well, this is the 0th graded piece of the Hochschild complex. You send that just to the circle with a single dot labeled by the element of A. what you send a tensor A to. Where you send it to a sum of two blobs. So this is a little diagram. This is meant to represent one blob diagram. This is meant to represent another blob diagram. So we have U1 and U2. And the blue things here are the actual blobs. Outside of the blobs I've drawn here, there are no labels. The pasting diagram is just empty. What's inside U1, we take MA and move A halfway around the circle, and in U2, we move A around the other half of the circle. These are both null fields. They both evaluate to 0, and you can see that the boundary of some of these two blobs gives exactly the same thing as the differential over in the oh, that's just the lowest degree one. What's another nice property? Well, so we expect for a TQFT invariant that homeomorphisms of the manifold act on these vector spaces that we associate with the manifold, just because you can push around these pasting diagrams by homeomorphisms. We get something better on the blob complex, which is that there's a chain map from the tensor product of singular chains on homeomorphisms of the manifold with the blob complex to the blob complex. So you should think of this as, say, if you were looking on a blob complex on a torus, and you look at some rational slope on the torus, that gives you a degree 1 raising operator on the blob complex, because the homological degrees you add to something, a one-parameter family of homomorphisms into something that makes degrees in the blob complex. Oh, and there are some nice properties of this map that it's associated up to homotopy and compatible with gluing manifolds together. So Kevin wanted me to mention this, which is in fact, only a very slight generalization of what was on the previous slide in some sense. So there's this thing called the Deligne conjecture, which roughly says that singular chains in the little disks operator acts on Hochschild's cohomology. So we can restate that slightly and then generalize it to arbitrary dimensions. So what I want you to, oh, geez, this slide is really not in the right order. Okay, well, you'll have to just ignore this N infinity here because maybe I can't really explain it without Kevin's talk coming first. But okay, basically, if we have some manifold M, and I want you to think an interval here. Let's call blob cochains on M some sort of homes from the complex associated to M to the complex associated to M. And this is meant to be something like where the usual blob complex is like Hochschild homology, this is like the first one. And so what we would like to say is that chains on the n-dimensional fat graph operad act on blob cochains. So it's a fat graph, or a single fat graph is what you see here. It has on the outside an incoming manifold, M3, an outgoing manifold, N3, and at various steps along the way, we cut out a piece M0 and paste back in a piece N0. So it's like doing a whole sequence of surgeries. We cut out one piece of the manifold and stick back in another piece. Okay? So that's a fat graph. And whenever you have an element of one of, or if you have a blob cochain for, well, say going from the blob complex of M0 to the blob complex of N0, there's a way of composing them according to a fat graph. And now, when you allow singular chains on this collection of operations that we have indexed by fat graphs, you can also have singular chains on this operator act on the blob cochains in a very similar way that we have chains of homeomorphisms acting on the blob complex.
What's that little asterisk next to the theorem?
Well, okay. So if you go and read the draft that's online at the moment, the proof of this theorem is about 3 lines long or 20 lines long and ends with a dot dot dot. And I think I would have to say that Kevin is much more confident in knowing how to write down what comes after the dot 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 than I am. And since I'm the one giving this talk, I should put an asterisk. Yeah, that's my guilt. But Kevin might not feel any need to put an asterisk if he was saying this.
I just did.
Well, yeah, I put the asterisk so that someone like you would ask. Okay, and I better finish up. A final nice formal property of the blob complex is that it's a gluing formula. You can compute the blob complex for a big manifold, knowing the blob complexes for the smaller pieces. So the idea here is that if you have a manifold which is just some codimension 1 manifold cross I, that blob complex naturally has the structure of an A infinity category, roughly given by gluing intervals end to end and reparameterizing intervals after you glue. Now, if you have a codimension 1 manifold Y sitting inside the boundary of some manifold X, that tells you that the blob complex for X becomes an A infinity module over this A infinity category coming from Y cross I. And the gluing formula tells you that if you have X with 2 copies of Y sitting in the boundary, you can compute the blob-homology of the manifold you get by gluing together the 2 copies of Y by taking an A infinity tensor product. Well, I mean, since there are 2 copies of Y in the boundary, the blob complex of X is a bimodule over this A infinity category, and we can take the self A infinity tensor product of that bimodule, and that computes the blob complex of the gluing together thing. And what that actually turns into in practice is telling you how to compute blob complexes by iterated Hochschild homologies. It might not look like it at first, but self A infinity tensor products are very much like taking Hochschild homologies of blob modules. And I'll leave it there. Thank you. Questions?
Wait till after part 2.
Well, part 2 will sort of be very different, so in particular, not.
Oh, yeah, dumb questions. And here you had D star of Y insert 0, 1, but then over there it says the module over.
Oh, okay. That was me being sloppy. I'm sort of implicitly saying, like, whenever you want to look at codimension manifold, some codimension manifolds across with the ball. So in particular, like I've said here, that Y across the interval is an infinity category. Kevin will tell you that if you have a codimension K manifold, the blob complex of Y across the K ball is naturally an A infinity K category. And so in particular, the blob complex of a point is some sort of A infinity version of the original point category that you put into the blob complex. Yeah.
So, in ecology, there's sort of 2 ways of building up more complicated spaces. One is by overlapping charts, and the other is by gluing cells together along the boundary. Is there some reason why you're taking the second route? For example, the reason I'm asking that question is the topological core manifold certainly has disk charts covering it, but it isn't formed by taking 4 cells and gluing them along the boundary.
It just seemed like gluing things along, compact boundary was easier, and never got around to thinking of the other way. But maybe that works too.
Okay.
I was just, I was wondering how the fat graph worked out as a generalization of the little visco gradient.
Oh, well, I mean, it's maybe not.
They just all those manifolds as zooms and ins.
Yeah, I mean,
if they're all
it's
balls.
a little bygone. It's a little bygone operator, maybe. I mean, if everything here is just an interval, then it's something very close to little disks.
Well, I think some top equivalent, I think, in the case where all the manifolds are balls.
So the blob homology of M is, I mean, it's like the M Hochschild homology of what your category.
Yeah.
And I'm wondering if there are things you can compute with this presentation of that. I mean, are there particular things you want to compute that you have in mind as examples?
Oh, okay. So, yeah, I guess I didn't say anything about the motivation for the blob homology in the first place. But the rough idea is that the TQ of T construction, where you just take all fields on your manifold and push it out by things that are that are locally null fields isn't an exact fund, because say we want to look at the TQFT invariant for some manifold with some specified boundary conditions, and we have some maps that modify the boundary conditions, and we on the level of fields, these maps were exact. When you go to the TQFT construction, you expect exactness to break just because you're taking a input. So the idea here is that this is a derived version of the TQFT construction. So for example, in either context topology or Kovanov homology, you can define either a 3-category or a 4-category, where you would like to produce invariants of 3 manifolds and 4 manifolds. But say in the Kovanov homology case, what you would like is an invariant of 4 manifolds with boundary, where in the boundary there's some link. The usual way that you compute Kovanov homology is by using the fact that you have a long exact sequence relating the Kovanov homologies of a link with a crossing like this and the link with the 2 resolutions. But if you're doing the obvious thing for a link in the boundary of some other 4 manifold other than the 4 ball, you don't expect that exact sequence to hold for the skein modules in another 4 manifold. And so the hope is that since this is the derived version, knowing the full blob complexes for 2 of those links, you might be able to compute the blob complex, or at least maybe only even the 0th graded part of the blob complex for the 3rd piece. So it's sort of intended as a saving exactness. And some nice examples of 3 and 4 categories that aren't semi-simple, strange triangulated.